Hey guys, welcome back to day 2 of limits. So before we get started with the new information, I'd like you to treat bell work every day like a mini quiz of the previous day. Sometimes it's a lead-in to future lessons, but most of the time it's a review of the previous day's lesson. So hit pause right now, treat this like a quiz, and see if you can answer these questions, and guess if you have to. Okay. F of negative 2 would be a solid point at negative 2, but at negative 2 there's a vertical asymptote there, so this does not exist. There is no point there. Okay, the limit as x approaches negative 2. Well, the limit from the left as x approaches negative 2 from the left goes to negative infinity. It goes down forever. The limit from the right as x approaches negative 2 from the right goes to positive infinity. It goes up forever. And those are different limits, so you should have said does not exist. Technically, infinity doesn't exist anyway, since it's not technically a number. All right, those two, maybe I tricked you on those. The next ones should be pretty clear. Okay, f of 0 would be a solid point at 0. So at 0, you have a hole here at about 1/2 and a solid point at 4. Well, f of 0 would be 4. Okay, the limit as x approaches 0, okay, well, the limit from the left would be 1/2. The limit from the right would be 4. Since those aren't the same, the limit does not exist. Okay, E. F of 2 would be a solid point at 2, and at 2 there is no solid point, so that one also does not exist. The last one, the limit as x approaches 2. Well, the limit from the left is 1/2. The limit from the right is 1/2. Since they're both the same and they're meeting at the same spot, even though there's a hole there, the limit does exist. And the limit as x approaches 2 is 1/2. Hope that went well. Okay, today's lesson. I'm going to take us back to the same problem we started with yesterday. We're going to do this from another approach. Okay, yesterday we approached this graphically and algebraically. Let's do the algebra first. The first thing I would do when I see a limit problem is just say, self, can I plug in x is 3? That's the first thing you consider. Pretend you don't even have the graph. Well, clearly I cannot plug in a 3 because there's a denominator of x minus 3, and if I plugged in a 3, that would give me a 0. So I would factor it. Okay, and when you factor it, you get this. Then I would cancel. And now I would try to plug in the x of 3 again, and we get 5. And that is the answer to the question. The limit as x approaches 3 is 5. And that is the algebraic approach. The graphic approach, the limit as x approaches 3, is the height we're approaching, and it's also 5. Okay, well now let's look at one other approach, which this is the approach that pretty much always works if you can use a calculator. I'm going to take this same equation and I'm going to plug it into my graphing calculator, and I'll show you how to do that next. When I plug it into my graphing calculator, like I'm graphing it, but instead of graphing, I look at the table function, it looks like this. Okay? Using the table function but counting by ones, I get this table. And I want to know what is the value or what is the height my graph approaches when x is 3. Well, when x is 3, there's an error because when x is 3, remember, there's a hole in the graph. Of course there's an error. So if there's a hole in the graph, we know that my calculator can't figure out the height when x is 3. But if you look at the table of values, you can see what it seems to want the height to be. The graph, the table is going from 2, 3, 4. It appears the next number would be 5. And in the other direction, 8, 7, 6, the next number would be 5. So you can use a table of values to estimate a limit as well. Okay, but usually counting by ones isn't specific enough. Usually even counting by tenths isn't going to be specific enough, but for this problem it was. Let me show you in the next problem how you could use your calculator to evaluate a limit. Okay, so this problem, I can't plug in 0 because that gives division of 0 in the denominator. I have no idea how else I can work this. I can't factor it. I'm stuck. So the first thing you're going to want to do, so I'm going to plug this into my graphing calculator, and even that, because of the fractions, even that can be a bit of a mess. Here's what that would look like. Okay, I put it in the y equals screen. The y equals button is in the top left corner right here. Okay, plug it into my calculator. The first thing I'm going to do is just look at the graph and remember that what this question is really asking, what is the height of my graph when x is 0? Okay, the limit is the height your graph is approaching from both sides, regardless of whether or not it actually reaches that height. So I'm going to look at this graph and see if I can estimate the height when x is 0. So first I hit the graph, and here's the graph. So when x is 0, does it appear that I can figure out what that height is right there? Okay, and it looks like maybe negative 0.5, but that's as accurate as I can get just by looking at it. So I now know, yeah, my answer is approximately negative 0.5. If this was a multiple choice test, I would see if that's good enough. All right, notice, by the way, it doesn't actually have a height at 0 because remember, there's actually a hole in the graph because you can't divide by 0. But it does look like it's approaching negative 0.5. All right, so how can I cheat and use my calculator to give me an even more precise answer? Right now I'm saying the limit is approximately negative 0.5. But maybe there's two answers closer to that. All right, here's how we could fudge that. I'm going to go to my table function, okay, of my calculator. And if I look at the table function and I count by 0.001s, okay, and I'll show you how to do that, then I get a better estimate. Now look at when the height, or when x is 0, what does my height appear to be getting closer to? From both sides, this way and this way, the left-hand limit and the right-hand limit, it looks like it's approaching negative 0.416 or 7, something in between there. And that's a much better estimate. Okay? To be even closer, I could count by even smaller increments. So let me show you how I did this on my calculator. Okay? When you go to table set, okay? Table set is the second button here above Windows. So you have to hit second first. I start my table at 0 because I want to know the limit at 0. And then I'm going to count by 0.0001. I'm really going to count by small increments. And then look at the table one more time. And notice now it's pretty darn clear that at an x of 0, my height is trying to reach negative 0.416. Okay? Oops, decimal's in the wrong spot. Okay, so that's how you use your calculator. If you have a problem, a limit question, and you have no idea what to do, put it into your graphing calculator like you're going to graph it first. Okay, just put it into your graphing calculator. Look at the graph. That helps you first make sure that the left-hand limit and the right-hand limit are at least approaching the same value. Then use the table function to see if you can figure out that missing number. Okay? That's pretty much my last resort when it comes to limits, because that's kind of a lot of work. All right, the next thing we're going to review is a couple more algebraic approaches to limits, because honestly, your AP exam is half calculator, half non-calculator. You can't use the calculator at all for a lot of the questions. So here's another example of a limit where if you had your calculator, you could do this problem the same way we just did. But there's another way to do this problem using algebra. So that's what we're going to do next. Hit pause if you need a break. Okay, so for this one, there's a radical within the fraction. Well, first of all, before I even get caught up with that, remember, your first approach to evaluating limits is to try to just plug in that number. Can I plug in x of 0? Well, if x was 0, then I'd get the square root of 1 minus 1. I get a denominator of 0, which you know you can't have, so that didn't work. And that does not mean the limit doesn't exist. That could mean there's a hole in the graph. And remember, a hole in the graph, whoop, from the left, from the right, a hole in the graph still means there's a limit. It's the height of the hole. Okay? So this doesn't mean there's not an answer. It just means I got to do a little bit of work to get to the answer. So here we go. How do we fix this problem when you have radicals? The key to this problem is to try rationalizing. Okay? What we're going to do is we're going to multiply by, I'll give you a hint. I'm going to go a little bit sideways for a minute. When you multiply something by like this, let's say I have x plus 5, this is a little sideways, times x minus 5. When you multiply two binomials like that, what happens? You multiply your first terms, you get x squared. Multiply the outer terms, you get negative 5x. Multiply the inners, you get positive 5x. Multiply the last terms, you get negative 25. What I want you to see is that those two middle terms go away because they're opposites. So when you multiply two binomials where they look like the same terms except the sign in the middle is different, it makes these two middle terms go away. It's the opposite of the difference of two squares when factoring. Okay? That's what we're going to use right here. Okay? So back to our problem. We're going to multiply the denominator here by the conjugate. It's the same two terms, the square root of x plus 1 and a 1, but we're going to change the sign in the middle to its opposite. That's what we're going to multiply by. That's called multiplying by the conjugate. Okay, and it's going to do some fancy stuff you'll see in a minute. Of course, we got to do the same thing to the top and the bottom or it's not legit. Okay, focus on the denominator because that's where the issue was. That's where we had division of 0. I'm going to FOIL. It looks messy, but it's no different than that problem we just did a second ago. You're doing the same as this, okay? No big deal. So, when I multiply the first terms, we're squaring a square root. Squaring a square root undoes it, and you just get x plus 1. The outers and inners, just like when we did this easier problem over here, the outers and inners are going to go away. I'm not even going to write it down. The outers are going to be a positive square root of x plus 1. The inners are a negative square root of x plus 1. They go away. Now the last terms, negative 1 times a positive 1 is a negative 1. Okay, that's my denominator. My new denominator. So a lot of people say it feels like you just squared this and this. No, that's not really what we did. We really didn't do that. That's not legal. What we really did was multiply by the conjugate, but it does end up looking like it has that effect of squaring, although that's not really the case. Okay, moving on. Okay, in the numerator, it's kind of hard to remember, but I don't want to do anything with anything in that numerator. In the numerator, I'm just going to keep it in parentheses and rewrite it all. I have an x, parentheses, bunch of junk inside the parentheses. Leave it like that. Here's why. Try to remember your whole focus, the whole goal in the beginning was we had a division by 0. I got to get rid of that problem. Well, right now in the denominator where I have that blue writing, hopefully this was glaring out at you, the plus 1 and the minus 1 goes away. Okay, and I just have an x. I'm going to rewrite this next step just for your benefit. So I have an x, parentheses, bunch of junk. And in the denominator, I have an x. Okay, oops, I made a mistake here. This was a 0. Well, my whole goal is to be able to plug in this 0. I did all that work. I still can't plug in the dang 0, but hopefully neon flashing lights are going off. Now, since I didn't do anything in the numerator, these x's cancel. So what I actually have is, you got to rewrite the limit. They're picky on the AP exam for free response questions. Now the limit as x approaches 0 of what is remaining. The remaining problem doesn't even have a denominator. Now I can plug in my x of 0. So by the way, you got to leave this limit symbol all the way up until the point where you actually plug in an x of 0. So now I'm going to replace the x with 0 right here. And I get the square root of 1, which is 1, plus another 1, and we get a 2. You have to leave this limit symbol all the way until the point where you plug in your x of 0, then you drop the limit when you evaluate it. And the answer to this question is 2. Now, do you remember how you could have checked it if you had all the time in the world? Put it in your graphing calculator and look at the graph, and it'll look like it has a height of 2 when x is 0. In truth, it doesn't really reach a height of 2. There's really a hole in the graph because those x's canceled. Okay, take a break if you need to. Hit pause. Okay, here's our last problem. One more type of simplifying in order to evaluate the limit. Again, first approach for evaluating limits, try to just plug in that value of x. And for this one, again, it gives us division by 0. So that doesn't work. We got to try some other trick. So for this one, when you have fractions within fractions, how do you fix it? Okay, the easiest thing to do for this one is, first of all, visualize another fraction here. And I'm going to basically get rid of all these fractions within fractions. And to do that, I want you to notice all of the denominators. I have an x plus 1. I have a 3 and a 1, not that that really matters, okay? I need to multiply by all of those factors. So I need to multiply the whole numerator by a 3 and an x plus 1. And if that 1 down here was anything other than a 1, I would need that also. Okay, so I'm going to multiply the numerator by a 3 and an x plus 1. And clearly I can't just multiply the numerator by that, so I'm going to do it in the denominator as well. Oops, that was messy. Okay, now this is legal. I'm allowed to do this because anytime you multiply by a number over itself, it just has a value of 1. So that's why we're allowed to do that. Okay, so what effect does that have? Let's get rid of that. I'm going to basically distribute this to both of these. Okay, so in effect, I end up multiplying the 3 and the x plus 1 times this guy, and I usually just write it like this, and this guy, and on the bottom. I'm going to pause for a minute and rewrite that because that's kind of a mess. Okay, so now we can cancel a bunch of stuff. These x plus 1s, one's on the top, one's on the bottom, and all we're left with is 3 times x. Here, these 3's cancel, and I'm left with a negative 2 times the x plus 1, which I could have distributed right then and there. On the bottom, nothing cancels, so I have a 3, an x minus 2, and an x plus 1. The limit is still out front. Okay, now remember, in the denominator, you really wanted this original x minus 2. Our goal is to really make that go away so I can plug in this limit of 2. So don't multiply out that denominator. We want that x minus 2 to stay factored. Instead, let's see if it just magically goes away somewhere along the line. We're going to distribute this negative 2. So I bring down the 3x. Distributing the negative 2, I get negative 2x minus 2. Well, when you combine those like terms, it's going to be just x minus 2. So now when I clean this up, I have an x minus 2 on the top, 3x minus 2 and x plus 1 on the bottom. And as you can see, like we wanted, the x minus 2's went away, which leaves nothing on the top, which means there's really a 1. So I'm going to rewrite my limit, pretty it up one last time. I have the limit as x approaches 2 of, if there's nothing on the top, there's a 1. On the bottom, I have a 3 and an x plus 1. So the x minus 2 went away, which is what I needed. So now I can evaluate the limit. Remember, on the AP exam, if this was a free response question, which in all honesty, this isn't really difficult enough yet to be a free response question, but it leads to something else in the future. Anyway, if it were a free response question, you got to make sure you have that limit right before you evaluate it. So now I'm going to plug in an x of 2 right here, which you don't have to show. I'm just writing that for your benefit. And 2 plus 1 is 3, so I get my final answer is 1/9. So the limit as x approaches 2 is 1/9, and that's my answer. Okay, I hope that went well for you. So now let's just basically summarize everything we've got, okay? Your overall approach for limits. If they give you the graph, then remember it's the height the graph is approaching from both sides, left side and right side. Sorry. It's the height your graph is approaching from both the left and the right, regardless of whether there's a hollow point or a solid point, okay? The limit graphically is the height you're approaching from the left and the right. Now, if it's not a graph and you're looking at the algebra, then your first approach is just plug in that number if you can. And if you can, like on this one, if you can plug in that number, then that just means your graph has a solid point there. Okay, if that doesn't work because you get division by 0, try factoring. Okay, that's this guy. And cancel and then plug in the number. If it has a radical in it, try multiplying by the conjugate. I would multiply this by square root of x plus 2 over the square root of x plus 2. Okay? If it has fractions within fractions, eliminate the complex fractions. Your last option, if nothing else works and you have no clue what to do, like on this one, graph it and see if you can estimate the height at 0. And if that doesn't work, look at the table of values. So that's everything. That's a lot of what we'll be doing with limits. Good luck with your homework. Here you go. Bye. See you next time.